Hi everyone. Today we're going to start a new chapter, chapter 10. This is our last chapter of the quarter. We're just going to cover this chapter very briefly, but it's all about radioactivity and nuclear processes. So some elements on the periodic table are highly unstable. And those elements want to become more stable. And in order to do that, they give off energy. Sometimes that energy is in the form of a particle or just energy waves. So those elements that are unstable have what are called radioactive nuclei. Now, this was something that a French physicist named Henri Becquerel was studying. So in 1896, he discovered that uranium compounds emit rays. And the way he discovered this was he placed the uranium compounds on top of a photographic plate. And usually when you're developing a photographic plate, you need sunlight, right? Or some sort of light in order for it to develop. But these uranium compounds actually developed the photographic plate without light. So that told Becquerel that there must be some sort of energy coming from that compound. And the photographic plate that was developed by that compound is shown below. And you can see some of his notes at the top there. So he called these rays uranic rays because he assumed that only uranium could emit these rays. Now, another scientist, Marie Curie, shown below, she did further research and found that other elements also exhibit this type of energy or these rays. And one element that she discovered was radium, and she named it for its green phosphorescence. And phosphorescence just means kind of a glowing effect. Now, some elements require sunlight in order to glow. So that would be like glow-in-the-dark stickers. You have to expose those stickers to light first before they actually glow. But radium could glow on its own without any sunlight. And for a really long time, radium was used on different objects like watches. And a lot of women were actually hired in factories to paint radium on top of things like watches. However, back then it wasn't known that radium was really bad for our biological molecules. And so the women painting these watches would lick their paintbrushes to get them into a fine point. So they were ingesting this radium and eventually became very ill. Thankfully, down the road, people realized that radium was really bad and toxic. So they stopped using it on different objects. But sometimes you'll find vintage watches and such that do have radium painted on them. And actually down below is an example of one of those watches. You can see it's glowing, and that glow is from radium, which is radioactive. She also discovered polonium, and she named that element after her home country of Poland. Now, she also did some of this work with her husband, Pierre Curie, but he died fairly young. Her daughters, which are shown in that picture below, one of them went on to become, I believe, a physicist. And Marie Curie and her daughter actually both were recipients of the Nobel Prize in chemistry. And then her other daughter wrote a biography of her mom. So they all did great things. And I think this is the first female scientist we've talked about. All right, so let's talk a little bit more about radioactive nuclei. So radioactive nuclei, again, are unstable nuclei that undergo spontaneous changes and emit energy in the form of radiation. So the emission of radiation by radioactive nuclei is often called radioactive decay. And down below is a periodic table, and all of the elements in yellow are radioactive. So these are the most common radioactive elements. Now, this periodic table is not quite up to date. You'll notice down here, we don't have very specific names for those last few elements, but that has since been updated in the last few years. So those elements now have actual names, not just unium or whatever those are. All right, so you'll notice the radioactive elements are all kind of towards the bottom of the periodic table. So really, radioactive elements, they have a proton to neutron ratio that's either too high or too low. So typically, these nuclei are trying to emit a particle to try to reestablish a stable proton to neutron ratio. So there are different types of radiation. One type of radiation is called alpha radiation. So alpha radiation consists of a stream of particles called alpha particles. Now alpha particles are identical to helium nuclei. So they consist of 2 protons and 2 neutrons. So down below we have a nucleus. And remember, a nucleus contains protons and neutrons. And this is an unstable nucleus, and the way that it will stabilize itself is by emitting a particle that has 2 protons and 2 neutrons. So you'll notice here we have a helium nucleus. So we can write this in isotopic notation, and we'll review isotopic notation in a bit. But again, remember that if you have 2 protons and 2 neutrons in a nucleus, then you have 4 total particles, and they all have a mass of 1. So the mass of this alpha particle is 4. Another type of radiation is beta radiation. So beta radiation consists of a stream of beta particles, and they are identical to electrons. So they are created in the nucleus of radioactive atoms when a neutron is converted into a proton and an electron. So this is really cool that this can happen in a nucleus. So down below we have an example of beta decay. So we have a carbon-14 nucleus, and one of those neutrons in the nucleus is going to turn into a proton by emitting an electron. And you'll notice we do have an isotopic representation of an electron there, but we'll talk about that in more detail in a bit. Okay, so remember, so far we've talked about alpha particles, which are identical to helium nuclei, and we've also talked about beta particles, which are identical to electrons. The next type of radiation is gamma radiation. So gamma radiation doesn't really consist of particles. It consists of high energy waves. So down below is the electromagnetic spectrum. So you might remember this from when we talked about electrons earlier in the quarter. And in the middle we have visible light. And then to the right of that visible light, we have infrared rays, microwaves, and radio waves, which all have low energy. And then to the left of the visible light, we have ultraviolet light, X-rays, and gamma rays. So these are high in energy. And in fact, gamma rays have the highest energy. Now, X-rays are just below gamma rays, and if you've ever gone to the dentist and gotten X-rays done for your teeth, they'll often put kind of a heavy mat on top of you, and that's to block any X-rays from penetrating into your body, and it's really to prevent your organs from being exposed to X-rays for too long. Now, if you get X-rays, it's totally harmless as long as they only expose you for like a second. But if you were exposed to X-rays for a really long time, so like minutes, then that could become harmful because they are very energetic rays. So gamma rays are even higher in energy than X-rays, so you can imagine that those are even more damaging. So once it was determined that radioactive decay or radioactive activity is dangerous to humans, there were some protections put in place surrounding those elements. Now, the use of shielding and distance are effective ways to prevent or minimize the exposure of individuals to harmful radiation. So alpha particles, those are really large compared to beta particles and gamma rays. I mean, they're actually very, very, very tiny for us, but relative to beta particles and gamma rays, they're fairly large. So these are relatively large particles, and that means it's pretty easy to stop alpha particles. You could stop an alpha particle with a piece of paper, for instance. So alpha particles, they're easy to prevent any penetration. However, let's say you accidentally ingest alpha particles or inhale them. Alpha particles are very damaging to our organs and our cells. They go through a process where they ionize, and so that can be very, very harmful. Beta particles are much smaller than alpha particles, so they can penetrate through paper, but they can be stopped by something like lead, which is a really dense material. And then gamma rays, remember, gamma rays are not particles. They're actually a form of energy, so they can pass through paper. They have to be stopped by really thick material like lead or concrete. And actually, when scientists, or let's say like at a nuclear power plant, if they've depleted a radioactive source, but they need to dispose of it, they'll dispose of it in a concrete pool almost. And the concrete blocks any residual radiation from getting out and affecting the land or the people who live nearby. Okay, so there are a couple more types of radiation. So the next type of radiation is positron radiation. So positrons are identical to electrons, except they have a positive electrical charge instead of a negative electrical charge. Now you might be thinking, so are they just protons? Because protons also have a positive charge. However, protons have mass. Positrons don't have mass. So the way that we write a symbol for a positron, we say that it's exactly the same as an electron, but it has a +1 charge instead of a -1 charge. So positrons are created in the nucleus of radioactive atoms when a proton is converted into a neutron and a positron. So down below, we have carbon-10, and one of the protons in carbon-10 turns into a neutron and then emits a positron. So a proton is losing its positive charge and becoming neutral. And then the last type of radiation is called electron capture. So electron capture is going to have the same exact result as positron emission. It's just a different process. So electron capture does not emit a stream of particles, but rather the nucleus is going to absorb an electron from one of the surrounding sets of electrons. So down below, we have the Bohr model of the atom, which we've seen before. And we've got our nucleus in the middle, it's blue, and some electrons in red. So if this nucleus is really unstable, what it might do, depending on the nucleus, it might grab onto a nearby electron and absorb it. So what ends up happening is a proton combines with that electron to become a neutron. So protons are positively charged, and then it grabs onto an electron which is negatively charged, and then their charges cancel out. So we end up forming a neutron, which is neutral. Okay. So I already showed you some isotopic notations for a couple of the different particles we talked about. So down below, I have a list of those different particles, and then the nuclear symbols or the isotope symbols for each of those different particles. So let's actually talk about isotope notations really quickly, and then we'll go back. So in nuclear reactions, specific isotopes of an element may behave differently. Now, remember, isotopes have different numbers of neutrons. So remember, when we were talking about isotopes a long time ago, we had, for instance, magnesium, and one atom of magnesium might have 13 neutrons, but another atom of magnesium might have, let's say, 12 neutrons. And so those two atoms of magnesium have the same number of protons, but a different number of neutrons. And remember, with a different number of neutrons, we're also changing the mass of each of those individual atoms. Now also remember that we have an isotope notation shown down below. So remember that we use the symbol capital A for the mass number of that isotope, and then we use a capital Z for the atomic number of that isotope. Now, for our discussion on nuclear reactions, we're also going to use the Z symbol to represent electrical charge. So Z will represent either atomic number or electrical charge. All right, so down below, remember that we can write the chemical symbol, and then to the upper left of the symbol, we'll put the mass number, and then to the lower left, we'll put the atomic number or the charge. All right, so let's go back a slide and look at the different types of particles that we might see in nuclear reactions. So let's start with the proton. Remember from a really long time ago when we were learning about subatomic particles, we said that we could use the symbol P+ to represent a proton. But we could also represent a proton in isotopic form. So we could either use H, because remember hydrogen has one proton, or we could just use, a P for proton. And then the mass number at the top left is 1, and then the atomic number on the bottom left is also 1. And again, that's just because we only have one proton, so the mass is 1, and again, the atomic number or the number of protons is 1. And then neutrons, we said we could use the symbol N0. But in isotopic form, we could write the symbol N. And remember, neutrons do have mass, so the mass number at the top left is 1. And then for neutrons, we don't have an atomic number because neutrons are neutrons, they're not protons. So instead, we're going to write the charge of a neutron in the lower left. And that would be 0 because neutrons are neutral. And then for electrons, we use the symbol E-, but in isotope form, or for the nuclear symbol, we'll use an E again, and then the mass number for an electron is 0, because remember, electrons are really, really small. And then we're going to, instead of putting the number of protons on the bottom left, remember this is an electron, so it's not a proton, we're going to put the charge down here, so that's -1. All right, now let's get into some of our actual radiation particles. So alpha particles we can represent with an alpha symbol. So that's our Greek alpha symbol. And then the way that we represent an alpha particle in nuclear notation, we can either use that alpha symbol or helium, because remember, alpha particles are identical to helium nuclei. All right, so then we have a mass number of 4 in the upper left because we have 2 protons and 2 neutrons. And so that gives us a mass of 4. And then the number of protons is 2, so we put 2 in the lower left. All right, next is the beta particle. So for this one, we're going to use the beta symbol, or we could also use an electron E. And remember, beta particles are identical to electrons, so we're just going to write a similar notation. But you could use the beta symbol if you want to differentiate it. And then positrons. Remember, positrons are basically the opposite of an electron. They also have 0 mass, but they have positive charge. So they're going to look really similar to the electron notation, but this time we have a +1 charge. Okay, so don't worry if you don't have that memorized. You can always reference this table if you need to. So how do we actually write what happens in a nuclear reaction? We're going to write an equation similar to how we wrote previous chemical equations, but instead of having the same number of atoms on each side, we're just going to look at the atomic number and the mass number. So the equation for a nuclear reaction is balanced when the sum of the atomic numbers of the particles on the left side of the equation equals the sum of the atomic numbers of the particles on the right side. And also, we want the sum of the mass numbers on the left to equal the sum of the mass numbers on the right. So let's look at an example nuclear reaction down below. So we have uranium, and it has a mass number of 238. So let's write that down. And then its atomic number, or number of protons, is 92. So uranium is number 92 on the periodic table. Now the products of this reaction, we have thorium, TH, and it has a mass number of 234 and an atomic number of 90. And then we also see that we're emitting an alpha particle. So this is alpha decay. And remember, we can represent an alpha particle with helium. And it has a mass number of 4 and an atomic number of 2. So remember, we want the mass numbers to equal on both sides. So on the left side, we have 238. And on the right side, 234 plus 4 is equal to 238. So they equal each other, which is good. And then additionally, we want the atomic numbers to add up to the same thing. So on the left-hand side, we have 92. And on the right-hand side, we have 90 plus 2, which is 92. So that's what we mean by balancing the nuclear reaction. Instead of making sure we have the same number of atoms on both sides, we're going to make sure that we have the same total mass number on both sides and the same total atomic number on both sides. So we're still following the law of conservation of mass. Now you'll also notice that we called uranium the parent nuclide. So basically it's giving birth essentially to new atoms and some radioactive particles. So the new atom that it formed, thorium, is called the daughter nuclide. So this is really, really cool because we started out with uranium and then we ended up with an entirely new atom. And remember, protons identify the elements. So initially we had 92 protons, which is how many protons uranium has. But once it emitted an alpha particle, then we only had 90 protons, which identifies thorium. So we have an entirely new element. Okay, so let's go through a few examples of how to write nuclear reactions and how to figure out, what the products are, or what particle is emitted or captured. So in example 1, we have bromine with a mass number of 84, and it decays by emitting a beta particle. And we want to determine what is the symbol for the daughter produced. So what is the other product? So let's start by writing out bromine's isotope symbol or nuclear symbol. So we said bromine has a mass of 84, but I can't quite remember the atomic number of bromine, so I'm going to pull up a periodic table. Let's go to ptable.com. So bromine is in column 7A, it's in the halogens, and it's number 35. So that means it has 35 protons. Okay, so let's go back and write that down. All right, and then we're told that it goes through beta decay. So it's going to emit an electron. Remember, beta particles are identical to electrons. So I'm going to write the symbol for an electron there. but you could also put a beta symbol in place of the E. So now let's figure out what is the other product. Now remember, we want the mass numbers on both sides to add up to the same thing, and we want the atomic numbers to add up to the same thing. All right, so down below, let's figure out the mass number of our product. So we have 84 on the left, and that should equal 0 plus our unknown mass number. Okay, so this is super easy, right? X is just equal to 84. So our mass number is 84. Now let's figure out the atomic number. All right, so we have 35 on the left, and that should equal -1 plus X. And X is our unknown atomic number. Okay, so let's rearrange. So we're going to add 1 to both sides. All right, so that tells us that X is equal to 36. Okay. So that makes sense because remember, during beta decay, we're turning a neutron into a proton. So we're gaining a proton. So if we look at our equation up above, we went from 35 protons to 36 protons. So that makes sense. Now let's look up atomic number 36 on the periodic table and figure out what our new element is. So right next to bromine, we have element number 36, which is krypton, Kr. So we're producing a noble gas in this reaction. Okay, so not too bad. All we have to do is some simple addition or subtraction, and then we also have to consult a periodic table if we don't have all the elements memorized. All right, so let's go through another example. Oh, here is the solution slide. So example 2, when samarium-148 undergoes radioactive decay, the daughter produced is neodymium-144. What kind of radiation is emitted during the decay? All right, so these are some elements that I never really use or think about. So let's try to find these elements on the periodic table. All right, samarium and neodymium. So these might be kind of towards the bottom. So let's look in those 2 rows at the very bottom. So kind of looking across the first row, number 62. So in that lanthanide row, samarium has the symbol SM, and its atomic number is 62. Okay. Now what about neodymium? That's number 60, so it's just to the left, a couple over from samarium. So neodymium has an atomic number of 60, and its symbol is Nd. All right, so we're dealing with some elements we don't normally deal with. Okay, so let's go back. All right, so we're told that samarium has a mass of 148, and we just saw that its atomic number is 62. And then we're told that one of the products of this radioactive decay is neodymium, Nd, and it has a mass of 144, and we saw that its atomic number is 60. And then we don't know what type of decay occurs here, so we need to figure out what that particle is. All right, so on the left-hand side, so let's figure out the mass number of our decay product. So we have 148 on the left, and then we have 144 on the right, plus our unknown mass number. All right, so let's rearrange. We're going to subtract 144 from both sides. And that tells us that x is equal to 4. All right. Now let's do the same with the atomic number. So 62 is on the left, and that should equal 60 plus our unknown atomic number. All right, so if we subtract 60 from both sides, we can see that x is equal to 2. All right, so thinking about the different types of particles that we saw earlier, we had alpha decay, beta decay, gamma radiation, positron emission, and electron capture. So this particle has mass, so we can already eliminate electrons and beta particles, as well as gamma emission, because remember, gamma rays don't have mass, they're just energy. So this would probably be an alpha particle, or we could also write helium there. Okay, so this goes through alpha decay. All right, let's do one more example. And here's the solution slide if you need it. And notice that they put an alpha symbol here instead of helium, so that's okay too. So in example 3, tungsten 175 decays by drawing in an electron from outside the nucleus in a process called electron capture. Write a balanced nuclear equation for the process. Okay, so this time we're considering electron capture. All right, so let's look up tungsten. That's an element we haven't really dealt with before. So let's see, tungsten. Tungsten is a transition element, so let's look in the middle. Its symbol is W, so tungsten is number 74. So that's one of those weird elements that has a symbol that doesn't really match its name. W might come from a previous name for tungsten. Okay, so the atomic number is 74 and the symbol is W. All right. And then we're told that it captures an electron. So we're going to write the symbol for an electron. And then we're going to try to determine what the product is, or what the daughter nuclide is. All right, so this is a lot easier because we're just adding up everything on the left-hand side, and then we're going to see what that equals. So the mass number of our new atom is 175 plus 0, so that's just 175. Super easy. Okay, and then the atomic number. That's going to be 74 plus -1. So 74 minus 1 is 73. Okay, so I don't know what element 73 is off the top of my head. So let's go look that up. What is element 73? So that should be right next to tungsten. All right, so it is tantalum. That's a cool name. And its symbol is Ta. Yeah, so with nuclear chemistry, we use a lot of elements that are we don't typically talk about. So we tend to kind of gloss over the transition elements and the lanthanides and actinides down at the bottom. So it's kind of cool to work with these. All right, so tantalum, that has a symbol Ta. Okay, so that is our new element after tungsten absorbs an electron. And that makes sense because during electron capture, a proton is turned into a neutron. So we're losing a proton and gaining a neutron. Okay. So we'll stop there today. And next time we'll talk about how radioactive elements have a half-life. And we'll talk about why that's useful. And then we'll also discuss some useful uses, or I guess, yeah, useful uses. It's redundant, but we'll talk about why radioactive decay can be useful in certain applications. So I will see you then.